Relative motion. Relative motion is nice and useful if you would like to combine velocities of particle or system or objects from a different reference frame. The notation that we're going to be using is very similar to the vector notation that we've been using before, mainly if you have, say, two position A and B, and you would like to express the position vector AB. So you're going from position A to position B. You can do it this way, following position vector AB, or you could decide to go through another point instead. So instead of using this path, you could use an intermediate, let's say go through point O first, and then from O back to B. Again, initial, final are the same. Therefore, you could use a displacement OA followed by another displacement OB, and this should still give you AB, just different path. Now, take a look at this equation. This left-hand side is actually nothing different than taking the right-hand side and sticking something in between. Hop. So you could go through point O, or you could go through point D. Same thing. This AB can always be decomposed as A blah blah plus blah blah B. In this case, I chose O, but I could have chosen D, like this, or several. First go to D, then to O, then to B. So I could have decomposed AB as AD plus DB, and then decompose, let's say, DB. Instead of going straight from D to B, I'm going to use O again, so I can decompose this one as AD plus DO plus OB. So again, just follow the pattern. We can now recompose this one. I have a D here, therefore this is the same as AO. And then again OB, which I could write if I wanted to AO minus BO, because remember that this vector is opposite to this one. This is AB, this is minus AB. So I could recombine those two as O here, AB, and again back to the same. So we are expert in this. The reason why I went through this is to remind us of the type of notation. We'll use a similar quote-unquote trick to express relative velocity. Let's take an example. Let's imagine that I am at rest on the ground, and I will define a coordinate system S, which is fixed relative to the ground. So I will associate my system S with the ground. So this system is not moving nor accelerating with respect to the ground, stuck with the ground. And that's where I am at right now. And I see a train passing by. Choo choo. Hop, hop, hop. With a particular velocity. Now I am measuring the velocity of this train with respect to myself. And since I'm in a coordinate system S, which is fixed with respect to the ground, really what I'm measuring is the velocity of the train with respect to the ground. Let's write it as v, velocity of the train, t, with respect slash to the ground, g for ground. Okay, so this gives us a little bit more precision in our way of describing velocities. Now let's imagine that there is a little biped in the train, and he or she decides to start moving, let's say, I don't know, in the same direction as the train is going. So now let's imagine that we were in the train, and I would like to describe the velocity of this man with respect to me, who is moving with the train. Now instead of using the coordinate system S, I'm going to use another coordinate system, which I will call S prime. And this coordinate system S prime is fixed, or is not moving nor accelerating with respect to the train. So this guy is fixed with respect to the train. So according to this coordinate system, which is where I am, fixed on the train, this little man or this little woman is traveling with a particular velocity, say traveling towards the right. So I'm going to write this velocity as being measured in a coordinate system S prime, which is moving with the train, as velocity of biped with respect to the train. Okay? Now, let's say I jump out of the train and I come back to my reference frame S. And now I would like to measure the velocity of that biped with respect to the ground. So really, I want the velocity of this little guy, not with respect to the train, I know that one, but with respect to the ground. How am I going to figure that out? Well, this is what we call Galileo transformation. I'm going to combine the velocity in different reference frame. So I'm going to use that technique. Remember A, B, I'm going to stick something in between. Same thing here. I'm going to stick something in between here. Like also general dx dy, you can stick something in between and use dx dt, dt dx. So you're just sticking something in between. Same thing here. Same thing as we did with position vector. I'm going to do the same thing here. I'm going to stick the train in between. So this will become velocity of that little biped with respect to the train. And since I finished with the train here, the next term will start with the train. And then this will complete. So let's look at this. This is telling me that the velocity of the biped with respect to the ground is equal to the velocity of the biped with respect to the train plus the velocity of the train with respect to the ground. So if the train was moving, say, at 20 mph, oh, hey, 200 mph, and the man was moving at 5 mph, then obviously with respect to the ground, you know from Galileo transformation, which is a transformation that makes sense to us, that the velocity of the man in the train will have 205. If the man was moving in the opposite direction, then you know that you would take 200 minus 5, same thing. But if we follow the math, we should end up with the exact same results. This is the velocity of the man with respect to the train, which is that one, 5. If I use this as my positive x, velocity of the train with respect to the ground, 200. Therefore, sure enough, I end up with 205. Again, if this guy was moving towards the left, this will become minus 5, this will become minus 5, and this will become y95, and so on and so forth. If, for example, you need this, but say you were given vgt in the problem, you know that the same way as this vector is opposite to this vector is the same with a negative sign. So you would just take the magnitude of what's given to you, multiply by minus 1, bang, done. We've just done in one dimension. You can extend the same concept in two dimensions. Let's say you're traveling in a particular velocity here, then with respect to a particular medium, air, water, then there is either some wind or some current that actually, you know, travels in a different direction. Obviously, from common sense, you know that your overall velocity vector will be, tilted by an angle. Same thing. You can just express each velocity vector with respect to a particular reference frame, combine them, rewrite them, and get the final velocity. And once you get this one, you can always deduce the angle of deviation. That's it.